Hello everyone, my name is Michael Horn, and today I will be completing my homework 3 part C for my process dynamics and controls class. And today in this video we have two things on the docket. The first thing is we will be using the Routh-Hurwitz criteria to find the maximum proportional controller gain in relation to the process gain for three identical first order systems in series under a closed loop control. And then the second thing, we will be then going into Google Colab and we will write a code to simulate the response slightly below, at, and above the Routh-Hurwitz bound for KC, which is controller gain, and to verify the stability characteristics computationally. So before we get into that code, we have to first use our iPad here. As you can see, I have labeled part C, and we're actually going to use a lot of the things that we used in part B from this video to maximize our ability to get this correct the first time. So let's begin. So now the first thing that we're going to do is go up to part B and bring down this solution that we already solved for, and that second, right? Okay, so and that is H3 is going to be equal to our KC value times K times A over 1 plus KCK. Now again, we arrived at this equation in part B from this homework, and now what we're going to do is we're going to go all the way up here to this, and we're going to use all of these values, and we're going to put this actually in the denominator of this new equation that we're forming. And so when you work this out algebraically, you arrive at the equation H3 is equal to this big denominator, and on the top we still have our KCK, and then the denominator, after you work out all of those terms we just said, you have tau squared s squared plus 3 tau squared s squared plus tau s plus KCK. And I'm actually gonna move this over. We ran out of room, so let's bring this down actually. Let's move this right down here, and so we can fit everything. So we actually have a plus 1 plus KCK, and then we actually still even have more to add to this. We're going to multiply everything by A over S. And so the last thing that we do want to note before we move into our, Routh-Hurwitz, that we're going to, let's just highlight it for simplicity. We'll highlight this bottom part, and we want to note that there are no positive roots. And so now that we have identified that and we have put together an equation, we can now finally work into our, let's make sure I spell this right, Routh-Hurwitz criteria. I did realize I was checking over this work. I did make a tiny mistake. These are meant, let's zoom in here. This is meant to be tau to the third, s to the third. So let's fix that up. Okay, and now we can move into the Routh-Hurwitz. To do this, it's going to be a very unique method. We're actually going to say our tau 3 minus 3 tau 0, 0. And then below that, we're going to do 3 tau squared, and then 1 plus KCK. And what you're going to do now is almost kind of cross multiply. So you go bring this over here, bring this down here, and then the final, you're actually going to bring this up here. And now from here, the purpose of this is to find three variables, and those three variables are B1, B2, C1, C2, and D1, D2. You can label these whatever you like. I just did B, C, and D because we already have our A value listed right here. So there we go. So now the first thing we actually want to solve for is B1 and B2. And through this adding and subtracting and bringing things over, you arrive, I'll skip the algebra, you arrive at a value of 1 and B2 to be 0. And now from that 1 value, you can write B1 is equal to this very long fraction in which you'll have 3 tau squared times 3 tau. And then you'll actually take away your tau cubed times 1 plus kck. And then in our denominator, we will have 3 tau squared. Now, for the next part, we will be looking for C1. And so our C1 value is going to be equal to 1 plus our controller gain value. And then you will actually also add it to 3 tau times our B2 value, which we now know is 0. So then you can say, okay, well, so then Kc is equal to 1 plus Kck, and this has to be equal to greater than 0 because our K1, our C, I keep saying K1, our C1 value is going to be greater than 0. So you realize, okay, Kck must be greater than -1. Now actually we can even break down this B1 term even more, and you arrive at B1 equals 3 tau minus tau times 1 plus Kck over 3. And so the next step for this is we want to set this equal to greater than 0 like we did with our C1 values. So you write 3 tau minus tau over 1 plus Kck is greater than 0. Again, break this down algebraically even more. You get 9 minus 1 plus Kck is greater than 0. And eventually you come out to Kck is greater than 8. I'm sorry. Less than 8. So now we've arrived at two values. We have Kc is greater than -1, but less than 8. I'll zoom out so you can see. And so now the final step is to say, okay, well, I want to isolate my Kc. And so we now know that Kc, our controller gain, must be greater than 8 divided by our K value. And now this is what we've been looking for the entire time, so I will box this out. It's not very good. And just to recap what we did, like I said in the beginning, we use our Ralph-Hirschowitz criteria to find the maximum. So this controller gain cannot be any greater than that in relation to the process gain, which is our K value. So this is our process gain, this is our controller gain, and this is how we are relating them in our 3 identical first order systems in series in a closed loop. And now we will be able to move into Google Colab now that we know this relation. So as you can see here, I've imported the CHE5 library, so we're able to complete this code. And so now, excuse me, the first thing that we're going to do is define all of our variables. And to do this, we obviously have our K, which is our gain here, and we'll set this equal to 1 to start this. And then we also have our controller gain, Kc, and this is where we will plug in the equation that we derived, which is 8 divided by our K value plus 0.1. And then we also need to define tau, which is going to be equal to 1.5 for this situation. So the next line of code that we're going to actually add is all of our equations, and this is GP, and the GP is I'm not connected to my iPad right now, but back in problem part 3, part B, we derived these equations from the system in which I drew a bunch of the tanks and loops. And so this equation that we got was tau times S plus 1 to the power of 3. And then we have GC, which is just going to be equal to our Kc value. And then our closed GC, which is closed, is equal to GC times GP in which GP is divided by 1 plus GC times GP. Now we need to say what we want out, which is our T and height. And these are going to be simulated, G closed, lambda, T from 1. We want 5,000 iterations. This is what that N equals 500, or N equals 500, 5,000. Excuse me, I'm tripping all over my words. And then we want with derivative respect to time, which is going to be 0.1. All right, and now the last thing, the most important thing, is we want to be able to actually look at this on a plot to see what is going on, which is fig equals make underscore subplots. And then we will do fig dot add underscore scatter. We want our x to be with respect to our x axis to be set to our time value. We want our y to be equal to the height. And then we want our mode to be lines. We don't want it to be dots. Okay, perfect. And then we need to update this. Update, just go to layout to make it easier to read. And we want to set our width equal to 600. And our height equal to 400. All right, so now we can plot this, run all, hopefully no errors. Always takes a minute. Well, yeah, it says we have an error here with our lambda. Forgot a comma. Oh, I spelled it wrong. Lambda has a B in it. Let's run all again. All right, so as you can see, this is a very stable graph. It's a continuous, the oscillations get larger and larger and larger. This is because we are within that value of Kc being less than 8 divided by our K value. And now, so let's check if okay, so it's at 1 right now, let's do 0.5. Let's see how this graph changes. Okay, it still is slowly getting bigger, but you can tell that it's becoming less and less stable as it is starting out large, and it continues to get large. It's not as it's not completely unstable. You can make it worse, but as you can see, it's going in the wrong direction. And so if you go down to a value of 0.1 and you run this, you get, okay, it starts out large, it gets a tiny bit bigger, but it is very, very unstable. And this is because you were working towards leaving that what's the word I'm thinking of? Threshold of being greater. It has to be less than 8 divided by K. So as you get closer and closer to being larger than that, it's going to become more and more unstable. So when we put this back at a value which is well within our stipulations, you're going to have more of the stable increase of oscillations. So thank you for watching, and this has been part C of homework 3.